All right, so basic concept of modeling. All right, so a differential equation is an equation that contains a derivative of an unknown function. And so basically now we're going to work calculus backwards a little bit. We gave you functions, you found the derivative, right? Now we're going to give you the derivative of a function. You're going to find the function. And it ends up being a horrible, horrible mess. Going one way is a lot easier than the other. Just all there is to it. Just a horrible, horrible mess. And so an ordinary differential equation contains one or several variables of an unknown function of a single variable. And so most of the stuff we're going to be doing in this class are ODEs. The difference, the other one, do I get into what a PDE is? Yeah, okay. So what are some examples of ordinary differential equations? Well, an ordinary differential equation is I can say the derivative of some equation, which I don't know, is equal to cosine of t. Well, you might actually know what that function is, but these can get a lot more complicated. I could say the second derivative plus 7 of the first derivative plus the original function is equal to e to the minus e2x. And so what's the original function? What is y, right? Well, this is an ordinary differential equation because y is only a function of x, right? In this case, y is only a function of x. In this case, y is only a function of t. How do I know that? Because I'm using my total differentiation symbols. I was using my partial, oops, I'm on the wrong layer. I was using my partial differential symbols, dy, dt. We have a completely different, oops, hi. We'll be in the partial land, okay? So these are ordinary differential equations. So they can look like this. Another way of writing this one would just be y prime is equal to cosine of t. Okay? So these are just some examples of what are differential equations.
What's
Yeah.
is that GL after the 7? Yeah.
Oh, no, this
Y
is
prime.
it's y prime.
Oh, okay. I'm sorry.
That's fine. No, it's not written very well. There we go. And then you'll have stuff that comes from physics, right? So you can have something that looks like this. And this is just an equation one of your books gives you. Does anyone know what this equation is? PDEs, and a little couple more stars, so I know what to do. All right, so partial difference equation is equations that contain one or more several variables of an unknown function, multiple variables. And so these are PDEs. And so some of you may know something like, I don't know, let's just write down one completely. So let's talk about the heat equation. So here, if I take the partial of U with respect to time, so our heat essence is minus alpha of the second order with respect to x, with respect to y, and respect to oops, z. Okay. And so we call this the heat equation. And so this is, and if I set that equal to something, this becomes a partial differential equation. So here, we'll be focusing on ODEs in this class. My PhD was in PDEs, but I used numerical methods, so I always just cheated the system, just how I did it. So the heat equation, Maxwell's equations, of course, are PDEs. because it's your electromagnetic field is based off your position and time. And so, and the change of that. And so that's another example of a PDE. It's a very popular PDE. It's actually the one I focused on. All right, so let's look at these for a second. So these are first order differential equations. Actually, let's make this an equation instead of an expression. So let's just set that equal to each other instead of setting it equal to 0. Just for my own sanity. All right. So the order of a differential equation is n, where the n is the nth derivative of the unknown of the highest derivative of the unknown function in the equation. That's a big mouthful. Basically, the order of an ODE is determined by the amount of derivative. And so here, this would be second order. All right, so we call this a second order ODE because the highest derivative here is 2. Here, we call this a first order because here is the first order ODE. And we call that because it hunts down all the Jedi in the universe, right? No. You guys are out of it. It's a Monday. I told you there'd be bad jokes. This is the first order because this is the first derivative in the galaxy. Sorry. Here, what order is D? What order here is D?
Second order?
Yes, this is second order. And the reason it's second order is because the highest derivative here is 2. Now here, notice that we're going to be using Roman numerals. So we use apostrophes up until 3, and then after that we use Roman numerals in parentheses to determine derivatives. So this is really the 4th derivative. This is the 3rd derivative to the 7th power. So this is 4th order. Okay, so that's where you determine order. So let's talk about what a solution is in the last 5 minutes, and we'll end on this page. All right, so a first order ODE, it's a function of its independent variable, the actual function itself, and then its derivative, and we set that equal to 0. Or often we just have the derivative is equal to some function of x and y, where x is the independent variable and y is the dependent variable. Some of these you can solve explicitly. You can write in an explicit form. Some of these you can't. Like this, there's no way of writing this as y equals something. And I think I need a derivative on that. Put a little derivative on the y's. Oops, hello. I think I forgot my derivatives on that. All right. So let's go back to the first one I gave you. What is y of t in this case? Or y of x, I guess. I think I always have x's or t's, and this book likes to use x's. What's y of x in this case? If I know the derivative is cosine of x, what's the function? It is sine minus sine of x. I have 1 vote for minus sine of x.
Yeah, it's minus sine of x.
So if I take the derivative of this function, do I get this function? What's the derivative of sine? Or minus sine? Minus cosine. So I want the positive, right? I want positive sine of x, right? So we're going to do anti-differentiation in a very interesting way. And so this one, you just literally anti-differentiated it, right? You just took the integral. The integral of cosine is sine, right? And so, but we also have to add plus c. So this is just a general solution, right? In this case, I could take my dy dx equal to cosine x. And I could literally split it as dy equals cosine x dx. Now, the reason we can do this, because this is some infinitesimally small amount of x, this is an infinitesimally small amount of y, but they are non-zero, right? And so I can just multiply this across. Integrating both sides is a valid function. I get y. Do this, I'll get sine of x plus c. Okay, so that's how we solved it, right? And to check it, we can just plug it in. Okay, and so we're going to be doing this. We don't need this. Bye-bye. Okay, all right, so let's, no, don't need this either. Bye-bye. All right, here we go. All right, so now we're going to talk about initial value problems. So initial value problems is you're given, it's kind of like when you're solving for your, when you're doing integration, we have that plus c. This helps you to deal with the plus c, right? So you're given some initial condition in order to handle that. So here, it's often in the following form. Here we have the derivative is some function of the independent variable x or t, depending on what I write in, and y, and then we're given some initial condition. And this is kind of like, it's like if I knew, and this helps you to solve a very basic problem. Say, hey, let's pretend I knew what the speed of a car was, or the function of a speed of a car, and I knew its initial position, right? Then you would, if I want to know where the car was, as long as I'm traveling in a straight line, it helps you to, you could clearly define the whole function where the car is at. Just be honest, but I'm only giving you the speed because the car would only spit out the speed for you, unless there's a GPS in it. So let's do this. My friend sent me a video of the new Tesla Model S that apparently goes from like 0 to 60 in like less than 2 seconds. It's like a 4-door, 5,000-pound sedan, just like rocketing down the highway. faster than like most production, like high-end supercars. I'm like, okay, you go have fun, Elon Musk. Send us to the moon because that's where you're taking us, right? Anyway, so let's do this. So let's solve this initial value problem. So so in the last page, we figured out what this is, right? The derivative of what function gives me cosine of x, right? And the derivative of that was sine of x, right? But we knew there was some constant here. We didn't know what that constant was. And so we got this from last time. But now we're going to add the initial condition. When y is equal to 0, we get 3 out. Okay. So how do we do that? Well, here we just plug it in, right? So here we just solve for c. So here, 3 is equal to the sine of 0 plus c. Well, the sine of 0 is 0, so that means c is equal to 3. And so now we have a specific solution, right? And we call this a specific solution. So we call this one the general solution right here. This is the general solution, or the general form of the solution. And here we have the specific solution. So I guess I should write that. That is the general solution. And this is the specific. I might have spelled that wrong. The chances of me writing words and them being spelled wrong are excessively high. I took first grade twice, and then I went to third grade. Don't ask. Just don't ask. It was some pilot program, and I got put in it somehow that the second graders would teach the first graders, so we're in the same classroom. It just did not end well, and I never learned phonics. But I don't know, something for me to work on later. All right, so let's look at this. Let's solve this initial value problem. So y of what function is going to give me 1.2 of that function? Does anyone know? if I take a derivative of a certain function, I get 1.2 of that function again. Does anyone know what that function was? Here we're just doing guessing.
Would it be 6/5x?
Yes. So 6 over, well, hold on. 6 over 5x. 6 over. So let's just wander through a couple. So I have this one in chat, 0.6. And I also have this one in chat, e to the 1.2x. So again, both of these answers from you guys. So let's take the derivative of this. If I take the derivative of this, I get 1.2 y. Well, is that equal to let's see. I want to see if I can correctly explain this. Yes, I think I'm okay now. Is 1.2y equal to 0.06y squared? Oh no, if I take this derivative, hold on. Let me back up. Hold on, let's do this very correctly. So let's take its derivative. I get 1.2y, right? Ah, I see what's going on here. This is not a function of y. This works, right? If y prime equals this, right? Hold on, let me see. I'm trying to explain. I know why it's not working, but it's not coming to me. Let me see if I can make it very, very clear. So someone says the function of y is equal to this. Am I allowed to do this? Can I say y equals 0.6y squared? Can I say this? Yes.
Plus c. No?
Well, can you say this? Does y equal 0.6y squared?
No, because y would have to equal y.
Yeah, so here, remember y is a function of something. Y is a function. In this case, let's make it x. Y of x is this equal to 0.6 y of x squared. And yeah, there's a value which makes this work, where you said if y was 0, right? There are values, but is this true in all cases? The answer is no, right? So let's say y of x is equal to the other solution. We got 1 point. Yeah. Okay. Actually, hold on. Let me do something. Let me do something real quick. That's fine. Let's do this. If I take its derivative, what do I get? I get 1.2. And then here, if I take its derivative, I get y prime is equal to 1.2 e to the 1.2x, which is equal to 1.2 times y, right? Which is the original function. Here, hold on. Let's see if I can do this. I don't know if I can. If I have some function divided by some function, I bet I can actually tease out that y of x equals to this in functional analysis. But let's not. Yeah, because here if I divide y from both sides, I get 1 equals 0.1. This is going to bug me. Yeah, no, this doesn't work. So let's get rid of it. Okay. So here we have this. We'll actually show you how to solve this in the next week. We'll show you how to solve this. So here we get this. So here, oops. So here we just have our function, and we just get this by guessing. But here we need the plus c, right? So here we're going to say our general solution here is e to the 1.2x plus c. Now, I can say E when x is 0, I get 3.4. So here I get 3.4 is equal. Oh, I remember doing something here. I'm going to write something, and I want to see if everyone's okay with this. And this is why I put this problem here. Is everyone okay with this and this being the same thing? As long as I say this is like C star, and this is just a normal C.
I mean, I've never seen that notation before, but okay.
let me.
I mean,
do
it's fine now. I just like I haven't actually seen that notation before.
Oh, okay. Let me do the intermediate step. So in plus C e to the C, right? And I'm going to say that C star is equal to e to the C. And the reason I can say this is given any number, I can tell you what e is to that number, right? And so once I do this, I can put it together. So this becomes, let me do this very carefully the first time, because I'm going to do this for like the rest of the class. Hold on. What am I doing? Hold on. I'm doing something not. Yeah, my brain's just full of guacamole today. I'm trying to. Hold on.
If you add them together like that, can't you, like with both the x, the 1.2x plus c in the numerator, can't you just technically multiply them?
Yeah,
Like
so
the convention, it's multiplying.
I know I'm doing something wrong. That's what's bugging me because it's wrong on my other notes. That's what's bugging me because it is wrong on my other notes. It means I taught it wrong. All right, I'm going to show you. All right, just for now, we'll address this when we actually address this. Let me. Why do I have white and white? Hi. Can I have my blue back? No. Can I have my blue back? Just accept that this is the answer for now. Okay. I hate to do this to you guys, but let's just do this for now. I will slowly build up why this is the answer when I analytically solve this. Since we don't know how to analytically solve it yet, that's not until 1.4 or 3 in this book. Since we don't know how to analytically solve this, let's go ahead and just assume this is the answer. And where it comes from is where, when I actually solve this through, is I get 1 over, when you actually solve this through, let me just show you the analytical solving. It's like, is there a good way to explain what I'm doing without solving it analytically? The answer is no. But how I'm solving it analytically is the following. And then I integrate both sides. And so I get ln of y equals 1.2x plus c. And then I exponentiate both sides and I get y equals to e to the 1.x plus c. Because I want to get rid of the y. I want y to be clean. And this is the same as e to the 1.2x times e to the c. And then you can just pull that out up front. Okay, so I guess I explained it to you. I was like, is there a way to explain how I get to this without doing that? And the answer was no. The answer is no. So this is how you solve it analytically. This is the first thing we're going to, this is the first method of how we solve it. So anyways, we get this to be the answer. Anyways, after we solved it analytically, let's do what we were meant to do. Does it make sense why this is this case now, where the C comes from? I think you guys did this maybe way back in the day, but maybe not. You may have never seen anything like this yet. I've seen it. Oh, okay.
So it's basically just because C is a constant and e to the C is a constant, it stays constant, so we can pull
Yeah,
it
so
out.
E
Right?
is a constant, so it's a constant, so it doesn't matter what
Cool.
you call that C. The reason it's multiplication comes from this instead of just adding it. When you solve it
I have a
directly,
quick question.
yeah, go for it.
Okay, so on the derivative of the y where you were showing on the right hand side, it says y, I just blanked, the derivative of y equals 1.2 e to the 1.2 x equals 1.2 y. Yeah, right there.
Oh,
So I am so confused. I don't know if I forgot or something, but how'd you get from there to there? The 1.2 e to the 1.2 x to
so here if I take
1.2 y.
the derivative of an exponential is a derivative e to the ax is equal to a e to the ax, right?
Yeah.
And so here, if I take this, if this is my function, I take its derivative, the 1.2 pops down, and I get e to the 1. So here, y derivative, or first derivative of y, is 1.2 e to the 1.2xx, right? Because of this rule.
Mm-hmm.
And then, well, what's e to the 1.2x? Well, that's y raised.
Oh, yeah. Okay. Thanks.
No. My brain's there too. We've all witnessed it, except I'm the one getting paid for this. so we get to this. Now that we established this and we've taught part of the other section, because this is how you do it, let's figure out if I plug in 0. So here I get 3.4 equals c e to the 1.2 times 0. What does that mean? Well, that just means 3.4 e to the 0 is just 1 is c. And so here you have your answer. And so you can get your specific solution, 3.4 e to the 1.2x. Okay? And so here we can take our initial value problem and plug in things, assuming you know the answer. All right, so let's build one model. Can I have my blue back? I lost my blue again. Let's build one. So create a model of radioactive decay where the amount of decomposition is proportional to the amount present. For the sake of the model, assume that we started with 1.5 grams of radioactive substance. Okay. And so what we're going to say is the rate of decay. So is proportional to the amount present. So here we're just going to make a model. So we're going to say the amount that we lose, or the change in my y, is some proportion to how much I have left, right? And since it's decay, we're going to make this negative. All right. So here we have this. From what we know before, if I have y prime equals some constant of y, this is the solution here is going to equal c e to the minus 0.5 kt. Okay. And here we're going to use y as a product of time. So we're going to have yt. That's why we're using.
Did you say 0.5 kt?
No, this is.
You didn't write it. Oh, okay, you said it and then you wrote something different. I was confused.
No. Oh, minus kt. I might have said 0.5. And then what do we have? Our initial condition is we start with, so at time, so y of 0 time is 0.5 grams. So what do we have here? We'll just plug this in for the initial condition. So we have y of 0 equals 0.5. I guess that's just kind of being redundant. E to the minus 0t, or minus k. I don't know what k is yet, but 0. This ends up being 1. So my specific solution here is, specific solution. I'm going to minus kt. All right. And so here we create this. And if we looked at that, that's going to look something vaguely like this, right? And this is radioactive decay. So you can use these to build, positions of cars or radioactive decay and all this other stuff. All right, so we're gonna learn how to solve differential equations, even though we didn't. I call this is an analytical solution. What we did right here is analytical. We just used the rules of analysis. That's why it's called an analytical, to produce a solution.